Have you ever wondered how an AI gets so good at a game it seems unbeatable? Or how a robot figures out how to navigate a messy room all on its own? Well, the secret sauce behind that is a really powerful blueprint called the Markov Decision Process, or MDP. And today, we're going to break down this exact framework, the one that lets an agent learn from scratch and actually achieve its goals. So let's start with the big question, right? How does a machine with no built-in strategy learn to play a super complex game like chess perfectly? How on earth does it figure out the absolute best move in any situation to give it the highest chance of winning? That right there is the exact challenge that reinforcement learning using the MDP framework is designed to solve. Now, to make this all feel a little less abstract, we're not going to start with chess. That's a lot. Instead, we're going to ground this whole thing in a game we've all played, tic-tac-toe. It might seem simple, but it's actually the perfect little laboratory for showing how an agent can figure out an opponent's weaknesses and genuinely learn to win, not just follow a bunch of rules someone programmed in. So here's the game plan for today. We'll kick things off with the agent's core problem, then we'll dive right into the MDP blueprint itself. After that, we'll talk about what actually makes a state good, how to find the best strategy, and we'll even look at an amazing real-world example. And of course, we'll wrap it all up with a quick summary of key concepts for your exams. All right, let's jump in. Okay, so before we can understand how an agent learns, we first have to really define the world that it lives in. And, at the heart of it all, every single reinforcement learning problem boils down to this fundamental interaction between two main players. On one side, you have the agent. This is our learner, our decision maker. And on the other side, you have the environment, which is, well, it's everything else. The agent takes an action, the environment changes, and then it tells the agent, okay, here's your new situation and here's a reward. The key thing to remember here is that the line between them is all about control. The agent controls its actions, but it doesn't control the outcome. Think about chess. The agent controls its own piece, but the opponent's move, that's part of the environment. So we have this back and forth between the agent and the environment. How do we describe that in a structured way? That is exactly where the MDP comes into play. It's the formal language, the mathematics that we use to lay out the entire problem that our agent needs to solve. An MDP is built from 5 core ingredients. First, you've got states, which are just snapshots of the world, like the layout of a chessboard. Then you have actions, the moves the agent can make. You have rewards, which is that immediate feedback, like getting a point. Then there's the policy, which is basically the agent's strategy or rulebook. And finally, you have the dynamics, which are the fundamental rules of the world. What happens when you take this action in this state? Now, for this whole blueprint to actually work, we rely on one super powerful assumption. It's called the Markov Property. All it means is that the current state tells you everything you need to know. The past, how you got here, is completely irrelevant. So why is this a huge deal? Well, because it means our agent doesn't need to remember every single move it's ever made. The current snapshot is enough to make the best possible decision. And that's what makes solving these incredibly complex problems even possible. Let's make this concrete with a couple examples. In a game like chess, the current board position is all you need. That's a perfect Markov world. But now think about draw poker. Your current hand isn't the whole story, is it? The history of how everyone has been betting is absolutely crucial. That's a non-Markov world. For what we're talking about today, we're going to focus on these clean Markov worlds. Okay, so our agent is out there taking actions and getting rewards. But here's the thing. The goal isn't just to snatch up the next immediate reward. The real goal is to get the most reward over the long haul. And this is where we hit a really critical distinction. This really boils down to a fundamental trade-off. Is it smarter to take a small, guaranteed reward right now? Or should you make a move that might not pay off immediately, but could lead to a much, much bigger reward down the line? This is the kind of strategic thinking that just chasing immediate rewards can't handle. And this is the absolute core difference between a reward and value. A reward is that instant hit, right? It's like pleasure or pain, it's immediate. But the value of a state, that's a far-sighted judgment. It's the total amount of reward the agent can expect to gather over the entire future if it starts from that state. A state could give you 0 immediate reward, but have an incredibly high value because it's the perfect setup for a future victory. It's all about playing the long game. So how do we figure out that long-term value? Well, this diagram here, called a backup diagram, gives us the clue. The idea is actually pretty simple. The value of taking a certain action depends on 2 things: the immediate reward you get, plus the value of whatever state you're likely to land in next. We're basically pulling the value from the future back into the present. letting that future potential guide our decisions right now. All right, so now that we have this idea of a value function, a way to judge the long-term goodness of any state, we can finally figure out the best possible strategy, what we call the optimal policy. The key that unlocks all of this is something called the Bellman optimality equation. Now, don't get hung up on the name or the math, just focus on the core idea with me. It basically says that if you have the perfect strategy, the value of your current state has to be equal to the reward you get for taking the single best action, plus the value of where that best action takes you. It's this beautiful, self-consistent idea that guides us to the solution. So how do we actually find these perfect values? We use an algorithm called value iteration. Imagine you start with a total guess for the value of every state. Let's say they're all just 0. Then you sweep through every single state and apply that Bellman idea to update its value based on its neighbors. And you just keep doing that over and over and over again until the values stop changing. Once they've settled, you found the optimal values, and from there, figuring out the best policy is easy. Okay, I know this can all feel a little theoretical, so let's ground this in a real-world example where these exact ideas led to, well, a completely jaw-dropping result. I want to introduce you to TD Gammon. This was a program developed back in the early 90s by Jerry Tesoro, and it learned how to play backgammon. To this day, it's one of the most famous, most inspiring early success stories of reinforcement learning. I mean, what TD Gammon accomplished was just groundbreaking. Get this, it learned by playing millions of games against itself, no human expert games required. It started with barely any knowledge of the game, and because backgammon has a ridiculous number of states, it used a neural network to estimate the value function. And the result? It reached the level of the very best human players in the world. It was an absolutely stunning proof that this stuff really works. All right, we have covered a ton of ground. So for all of you who are studying this stuff, let's bring it all home. Let's condense the most critical ideas into a single, super focused summary. If you're studying for an exam, this next slide is your golden ticket. Okay, here it is, the rapid-fire review. The agent/environment setup is the problem framework. The policy is the agent strategy. The value function is how we predict the future. The Markov property is the key assumption that makes it all solvable. The Bellman equation is the math that defines optimality. And dynamic programming, things like value iteration, are the tools we use to actually find the solution. Got it? Good. And you know, this all comes back to a core philosophy, which is captured perfectly in this quote from the textbook by Sutton and Bardo. Unlike other types of machine learning, reinforcement learning doesn't just solve one little piece of a puzzle. It starts with the whole shebang, a complete agent, interacting with its world, trying to achieve a goal. So, at the end of the day, remember that the Markov decision process isn't just some abstract theory. It is a powerful, practical blueprint for building intelligent agents that can genuinely learn and adapt in complex worlds. And that leaves me with one final question for you to think about. Now that you have this blueprint, what intelligent agent would you build first?